Here's a simulation of Charles' law, where you look at the scale at the bottom and you slide the button all the way to the left or right, and we're going to slide it to the right, and then we'll see what happens to the temperature and the volume. So let's take this, slide it up here, and let's see what happens with the graph. You can see how the temperature is increasing, and so is the volume, just like we said. This may or may not work on your computer, but it's a good illustration here. The greater the temperature, the greater the volume. That little mass is there on top of the, let's see, top of your scale here. The mass is not doing any work on this. It's moving slowly enough that the only energy into the system is coming from the heat inside the volume of gas. So this is kind of neat. Hopefully it works for you, but if not, you do see the linear relationship between the volume and the temperature. Let's see how this works in something we might see every day application. Soaring birds like the California condor, here's two of them, they rely on hot air rising in order to stay airborne for long periods of time without having to flap their wings too much. Can you explain why hot air rises uses Charles's law and the concept of density? Take a few seconds, pause the video if need be, and then you can move this box for the answer. Okay, here we go. Let's move this off to the side. As the sun warms the earth, the temperature of the air increases. That increases its volume. Therefore, its density is decreased compared to the air around it. Now, these updrafts, that means the warmer air goes up. They're not everywhere, and they're often broken up by cooler air returning to the surface, right? Because if the air just kept going up, we'd wind up with no air. But the higher it goes, cools down, comes back down, and you get downdrafts, and the condors are pretty good at figuring that out. On to the third law. This time, we will keep the temperature and pressure constant. And we're going to find that the volume of a gas is directly proportional to the number of moles of a gas. The more particles that are present, the more room they will need to move around if the pressure is to stay the same, because you only want so many of them to hit the sides of the container at one time. So if you add more, you need a bigger container. So over here, we have 2 liters, and we have 4 moles of gas. If we expand to 4 liters, we can hold 8 moles of gas. So since it's directly proportional, we go from V is proportional to N to V is equal to some constant, a proportionality constant. This time we'll call it A, probably for Avogadro. V is equal to A times N. Just like in Charles's law, where we have this direct relationship, and this time it's between the volume of a gas and the number of moles, we can just draw a plot of the volume versus moles. We don't have to take the reciprocal of either one of them, because if you look up here, V equals AN, looks just like Y equals MX. So M, the slope of that line, will be A, the proportionality constant. One more law. This time, we'll keep the moles, the number of moles, and the volume constant, and we're going to vary pressure and temperature. What we find is that the pressure increases proportionally with the temperature. The faster the molecules move, the greater the force of each collision on the container. That increases the pressure, right? Because the faster they are, the greater kinetic energy they have, 1/2 mv squared. That you have greater energy, that will also increase your pressure because they'll hit the walls with a greater force. So let's take an example here. Pressure, 32 millimeters of mercury at 200 K, 200 Kelvin. If we increase the temperature, these guys are moving faster. You can see how the vectors are bigger. That represents their velocity. And that will give a greater pressure. There will be more energy in the collisions. The pressure will be greater. Once again, we have a direct relationship, so we can just go ahead and plot the variables against each other without taking the reciprocal of one. Remember, we did that in Boyles's law to get rid of that curve. So this is Gay-Lussac's law. Pressure is some proportionality constant K times temperature. We plot pressure and temperature. we get a straight line, and the slope of that line is equal to K. If you watch NASCAR, you will see an application of Gay-Lussac's law. The mechanics have to be very careful to adjust the pressure of the car tires during the race. Using the concept of friction and Gay-Lussac's law, what do you think happens to the air pressure in a car tire over the course of a long race? So take a couple seconds, minutes to figure it out, and come on back here when you're ready. You can pause the video. Okay, let's see what we got. What is the frictional force between the tire and the ground going to do? Well, it's going to increase the temperature of the tire, and according to Gay-Lussac's law, that will increase the pressure. Now, you can't do that too often because if the pressure gets too high, evidently you can probably burst the tires. And in addition, as the pressure increases in the tire, the traction decreases slightly because the volume of the car tires does change a small amount. And you don't want to decrease your traction because then you don't keep going straight and you might lose control of your vehicle. So the mechanics continually have to adjust the air pressure when the cars come in for their little pit stops. Summarizing everything we've talked about on these four variables, this fantastic little chart here. On the left, we talk about the two variables that we're looking at that can change. Here are the two variables that stay the same, and we have a total of 4, so clearly 4 minus 2 is 2. This I find very interesting, the relationship. There's only one that has an inverse relationship, and we'll get to there when I hit the graph. Here's your mathematical relationship. Okay, you can see the inverse. You have the two variables multiplied by each other. When you have a direct, you can see that they're divided by each other. Inverse is the most interesting because if you just go ahead and plot pressure and volume, you get this curve here, okay? Pretty hard to find the slope of that because it keeps changing. So what we do, we like straight lines, we would take the reciprocal of one of those, plot that, and typically I think we took the volume. We could go either way. You will get a straight line, you find the slope, and that'll give you your proportionality constant. When you have direct relationships, you just plot the two variables and you get a straight line in each case. And then you can directly find the proportionality constant. Time to start setting up some calculations. This won't be as intense as the stoichiometric calculations from the last chapter, but we do have to calculate. That is the basis of science. Quite often, one of the variables we use to describe a gas changes as a result of some chemical reaction or an environmental change. We can use the gas laws that we just came up with to calculate the new value for the variable. You have to choose which gas law is appropriate due to your conditions. And just a quick nomenclature thing, value 1 is your initial condition and value 2 is your final condition. So here's Boyle's law. Remember we said it was equal to a constant? Well, if it's equal to a constant, your before and after have to equal the same constant, so you can set them equal to each other. So P1V1 is P2V2, and that is our indirect relationship. Avogadro is a direct relationship. The volume over the number of moles in the beginning equals the volume over the number of moles in the end. Charles' law, V over T, V1 over T1 is V2 over T2. And then finally, Gay-Lussac's law, P1 over T1 equals P2 over T2. It is always good to have a procedure or a process to do calculations. So we're going to show it right here. We're going to start with the question. We have a 13 milliliter balloon at 34 degrees Celsius, and it's heated to 78 degrees Celsius at a constant pressure. Assuming no molecules escape or enter the balloon, what is the new volume? Procedure. Identify the quantities given and determine the unknown. That's the first step in darn near any physics or chemistry problem. And here's the key. You have to convert degrees Celsius to Kelvin or it won't work. Pressure or volume measurements can stay the same because they're going to cancel out anyway. Decide which gas law to use, and you have 4 of them. Predict what impact the change will have. Will the variable go up or go down? This is a good way of checking your math. Rearrange your equation, isolate the unknown, and then perform the calculations and check your answer, both mathematically and your intuition there. You're thinking about what should happen based on the equation and based on your knowledge of chemistry. Let's solve the problem using our process. So the first thing we do is we find the givens. And here are the givens. Okay, we have V1, T1, and T2. What do we do with degrees Celsius? We convert it to Kelvin by adding 273 to it. So here's our temperatures. And then what's unknown? Well, they're asking for the new volume. Another name for that is V2. So that's right here, kind of obscured by that one line. What gas law are we going to use? Well, we have volume and temperature are the variables, so that's Charles's law. We now want to predict what will happen. Well, we know that volume and temperature are directly related. Therefore, the volume of the balloon should increase with the increasing temperature. Last step, rearrange the equation to isolate the unknown. Okay, so what did we have here? I'll just show you the original equation and show you what not to do. We had V1 over T1 equals V2 over T2. We're trying to find V2. Now, a lot of people, and sadly you might be one of them, would go ahead and just plug in V1, plug in T1, then plug in T2, and then do the math, multiply the number down here, the T2 times V1 over T1, and that gets messy. And it may work, maybe fairly easy for equations like this, but the more complex equations you get, you want to solve for the variable first. This way, if you make a math error somewhere, your teacher will be more inclined to give you partial credit because you show something like this. You show that you understand what's going on. And also, this does help you keep track of your numbers better. So we go ahead, rearrange it to solve for V2. We then substitute in the numbers. And you want to do this step and then this step because now you've got most of the credit for the problem. And let's say your calculator isn't working right or you put the numbers in wrong and you get an incorrect answer here. You've done everything except the final math. Most teachers will only take a point off of that. Okay, now let's do our check. After that little advertisement for solving for the variable and isolating the unknown, we get 15 milliliters. Does that make sense? Yes, the volume has gone up because the temperature has increased. That was our prediction from the previous slide. Let's illustrate another problem. We have a rigid gas canister. Well, it's already in bold, but let's circle it too. Has a volume of 18.5 liters at 13 degrees Celsius, and the pressure gauge reads 45 atmospheres. To what temperature would the gas need to be decreased to cause the pressure to read only 30 atmospheres? If the canister is rigid, can there be a volume change? Well, let's start with that first question there before we go on to the problem. Rigid means the volume stays the same, right? Because the gas is going to expand to fill the whole gas canister right in the beginning. Then if it's rigid, it can't expand anymore, nor can it contract. So let's see, we'll write the answer here. Nope. We just write no. We write our givens. Notice what did we do with the Celsius? Turned it into Kelvin. So here's our initial conditions. Here's our final conditions, and we have one unknown. So take a couple seconds or minutes, work it on your own, and come back when you're ready. We'll move the tab. Okay. So we use our three-step process. We find that pressure and temperature are the variables, so we want to use Gay-Lussac's law. And we're going to predict that the temperature will be lower because it's a direct relationship. Isolate the variables. Please isolate the variables. Now put the numbers in. You're most of the way home. Notice we didn't have to worry about converting the pressure because the pressure units cancel out. And we get a final temperature of 190 Kelvin, which is lower, so it makes sense, makes physical sense. So that's pretty good.